Welcome, this is Chris from Modka Games. Gonna try something a bit different today. So quite often when I start my programming sessions, I like to start off with just a little bit of a warm-up exercise just to kind of make sure everything's all ready to go. And I thought I'd walk you through the kind of thing that I normally do. So what I've got here is just a little bit of code that we found online. It's a binary search function. As you can perhaps see, there's some little problems with it. That's okay. Most code has problems of some sort. But I'm just going to walk you through how I convert some code like this, once I've cleared the licenses and so forth. If I wanted to put it into a format more friendly to what I normally use. So this is my text editor that I use quite often. What I've done is just grab that code and put it right in here. First thing I'm going to do is just see if we can get it to run and see what happens. So as you can see, we've got some output, and it looks like there's some bugs, but it's okay, we'll fix them up as we go along. So first problem, function name here is called research. I don't know if you guys know the research function. It's actually occurs in a seminal paper that talks about how to do algorithms which take forever, even though they appear to go quickly. So the first thing we're going to do is we're just going to call that function binary search instead of research. Just fixing up some formatting here. You see here we're passing in a parameter here by an array value. Now normally we don't like arrays. Arrays are actually very similar to pointers, but they have some minor technical differences with functions like, with built-ins like size of. Pretty much anytime you use an array, you can also just use a pointer. But the converse isn't quite true because of some name mangling problems. Just going to fix up some white space here. Let's just have a quick look at this algorithm. So what it's doing is it's trying to do a binary search over this array here, this A parameter. You see we compare if it's in the middle. If it's in the middle, we return the result because we've terminated the algorithm. And then we either go down the left path or the right path, and we've got the result here. We know kind of ahead of time that we're not going to need this final index value. We're just going to return straight away, so let's just go ahead and get rid of that. We'll keep this in for debugging just at the moment, but we'll probably get rid of that later too once we know that it works. So this next line is kind of interesting. Let me just call your attention to this. This is kind of one of the classic problems of binary search. So if these numbers here, low index and high index, if these numbers are large, if they're bigger than 2 to the power of 31, a 32-bit integer here, then this can actually overflow and we can get a bug here. So we're just going to fix that up immediately because we see that. So the way to fix that, there's quite a few different ways. But one way is to go like this. So we're going to take the difference of high index and low index. We're going to divide it by 2. And then add that on to low index. And that way this will always stay nicely within our range of integers. We can actually also speed this up slightly because we know that integer division also has to check for negative numbers and do some strange things. So we can speed that up slightly by using the shift right operator. Now I know what you're thinking. Where'd that shift right operator go? So that's something funky my text editor does. So if I have a greater than sign and another greater than sign, and if I put them together, then I just get this symbol here. Now the ASCII is still underneath, it's still doing the two greater thans, but it's just putting that on screen in an easier way to visualize. So let me just show you one more time. So I've got my two arrows. If I put them together, I get a different symbol on screen. Underneath, again, it's still using that same representation. So now here what we have is we have this array lookup, A mid-index, and we see that it's used twice. Now, normally a good compiler will be able to optimize that out and just use one lookup instead of doing two lookups. However, sometimes that's not the case. So in order to make life easier for the compiler, we're just going to go ahead and make that lookup. So we don't have to worry about whether or not the compiler can optimize it or not. Now something really interesting just happened while we changed that. So we've changed that over, but you can see here that it doesn't quite line up. And that's because, here, let me just switch this on. You can see here this is 4 spaces and what happened is I've inserted a tab instead. Now, some people like their tabs to be 3 spaces, some like them 4, some like them 8, some like them 2. My tabs are 3.5, and that's so I can immediately tell if I have a formatting issue. So let me just go ahead and I can fix that straight away, and we've fixed all those tabs, all those spaces into tabs automatically in the editor, just an auto editing feature. Cool, so now we've gone and hoisted that, that variable there. I've got that into a temporary. Let's have a kind of a closer look at what's actually going on here. So if the mid value is equal to the target, then the final index is the mid. Well, okay, we may as well just return at this point because we already have it. We already have the answer, so there's no reason to do any further processing. Let's just tidy that up. Now, we should never do the debugging right here inside the function. What we really want to do is we want to put that here where it's called. And we'll just put that there for later. We'll come fix that up when we come change the caller. So this is starting to look a bit better already. So if the mid value, So again, if I have 2 equal signs, one after the other, and I contract them down, I replace it with this symbol here. So again, this just helps with pattern matching, so that we know that if we see this equals here, we know that this is an equality operator rather than anything else. And that means we're just not going to confuse that with any other operator, because we can immediately do pattern recognition on that if we see it often enough. Again, this is just in my text editor. Your text editor is obviously different. So we had an if, and then we have the else, but we know that we have a return here, so this else is actually unnecessary. So we'll just go ahead and clip that straight out. We don't need that. Okay, what have we got now? So if the mid value is less than the target, we're going to do binary search instead of research on one side of that. Now then, how can we clean this up a little bit? Well, let's see, we'll just fix this up here. So if it's less, we can do that, or otherwise we can do this. Well, part of the problem here is we're getting all these indices messed up, and it's starting to be a bit confusing. So instead of passing in the base of the array and these indexes, what I'm going to do is change it to be more iterator style. And what instead we're going to do is we're going to pass a pointer to the lower value and a pointer to one past the end. So this is the terminator value that's just off the end of your array. So this is your STL begin, and this is your STL end function. So let's go and we can fix this up a little bit. So this is now a pointer as well. And we can just do a same pointer math. It just works out the same. Clean that up. Clean that up. Notice this this debugging is not going to work here. We're not going to get good numbers out here, so we'll just trash that. If we need it later, we can come put that back in. And then the mid value, well, that's quite easy. That's just star mid. And mid value less than target. Great. Okay, now let's fix these up here. So we're searching for our target, and on one end we're going from, let's see, we're going from, this is going to be mid to upper, and this one here is going to be lower to mid. See how much easier that was? Now here's something that's quite interesting too. So if our mid value is less than our target, we're going to be scanning the upper end of the range. Okay, now I don't like scanning the upper and then scanning the lower. So let's just flip this if statement around. So now we have lower, and then we have upper. But in order to do that, we need to flip the sense of that. So we just transformed that code. We didn't actually change anything. But now we have lower to mid and mid to upper. It's a bit more clear in our head what's going on. And actually, just because I like less than much more than I like greater than, it just seems to flow a bit easier. If target's less than the mid value, we're going to scan the lower end, and if otherwise, we're going to scan the upper end. Now then, I think I spot a bug here because there's a chance we could fall through if there's a mistake. So what instead we're going to do is if this fails, right? So if upper and lower are the same, then mid is going to be equal to lower. And if upper is 1 past the n, which means that we're actually at the end of the array, then it looks like we've got our termination condition. So our termination condition is just going to look like this. If mid is equal to lower, then we're going to want to return. What are we going to return? Well, you see, if we have a mid, let's return. Let's just return mid. Why not? Oh, but we need to check. We need to check if it's actually equal to target. If it's equal to target, we'll return mid. Otherwise, we'll return a null value there. Right. Now it turns out we don't actually need this clause anymore. And look what we've done. Look what we've managed to do now. So if the target is less than the mid value, we scan the bottom end. Otherwise, we scan the top end. Brilliant. So I think we're pretty close to finished on this function. We just now need to go and write some tests to make sure that it is actually computing what we think it's going to compute. So mid value, star mid, isn't it? Right, so the result from this is now an integer pointer. Uh-oh. We just found a variable called array. Now, array is type. It's like calling a car or something like that. I mean, it is actually an array, but it's very poor form to call it such. We want to stay away from variable names like array, list, integer, float, anything like that. We want to call our names actual real names like Harry, Fred, Camilla, anything like that. We didn't need that +1 there. Who needs a +1? Right, so we're going to call this function binary search with some parameters, which is going to be, in this case, 234, data +0, and data +1000. Remember, because we pass the end one, the one just off the end. Now, if we want the index, we can just go result minus data, assuming it's non-null. Let's extract that out. Final index. Now, I know what you're thinking. You're thinking that's pretty unreadable. That L and that I look really close together. But you know what? We don't actually need to call it final index. We can just call it index because we're up in the parent function. So the final index, no. The index is, well, look at that. Looks like it didn't work. Alright, so should we try and find this bug? I'm guessing there's a good chance we might have this around the wrong way. Let's give it a shot. Still no good. Well, let's put some debugging in then. So I'm a big fan of printf debugging, but let's see how we go. So we're just going to record some numbers here. So start low and start mid. So we're getting close, 323, so that does look like the number we're looking for. There's 324 and there's 324. So what happened? Well, let's try that. There we go, it's a bit more like it. So now we have our function, but we really want to do a few tests just to make sure that we're actually getting it correct. So let's try fix this up a little bit. I'm going to use a smaller number here, just so it runs a bit quicker. We want to avoid numbers like 1000 or 1024, especially with a binary search. Okay, so, and then this of course is n, and we'll put that in there. Okay, great. So, we may as well just test all of them. So we've got, let's start with the lower limit first. We'll just go from I to n. And then j to n as well. And let's just start with a silly number first, one that we wouldn't expect to be in the data. So what we're expecting here is we're really testing the n conditions. So in this case, -5 is guaranteed to be smaller than anything in that loop, and we're really expecting this to be a failure condition. And let's just print that out to start with. Now you see here I'm putting it on the left of the screen, which means that this isn't code that I'm happy with. It's just code for testing. And we see we get a whole bunch of zeros, so that's great. So we're just going to go ahead and assert that that's the null pointer, so then we know for sure. And it looks like we're missing assert. Let's just get assert in there as well. Assert.h, I think it's called. I keep changing the names on me. Cool. So now we have our assert. We've actually checked this twice. You see, we've checked it once with the printf, and then we put the assert in just to make it even stronger. Now that we've done that second check, we can take that out. Now we also want to do one for the upper end, just to make sure that we're checking the upper bound correctly. So let's do n plus 5. Great, we're all good. So now let's do one last loop over all the variables. Just make sure that we can find them all in that binary search. And so the value is going to be binary search, and we're looking on k with data plus I and data plus j, so we're scanning over the entire range. And for this one, we're just going to do a more traditional check, because here what we're doing is we're checking the boundary cases are correct, but here we're actually checking that the algorithm itself, and so we actually want a different style of check. We want it to be equal to k or not equal to k, as the case may be. And if it's not equal, we're going to say a failure with those parameters that we just checked. And sometimes I quite like to do this more like a JSON style. So we've got like a I is %d, a j is %d, a k is %d, and so we're just gonna have a slightly different convention here when we're outputting the results. And this is kind of more suited to being interpreted into a spreadsheet kind of example. Now we just ran that and we got no output, and that's good because it means it all completed correctly. But now we need to test our test cases. So instead of having not equal, we're just going to replace this to equal and confirm that all our test cases now fail. And so when we run that, we see we've got lots and lots of failure cases. And that just gives us confidence that our test is actually testing what we think it is. So now we've got some pretty good confidence that this function is actually working. We're just going to use a few different values of n here, just to try it out on a few different things. So great, it's working for 3, it's working for 300, it's working for 256, we'll try it. Cool. So some people like to go ahead and put this kind of thing into a proper unit test, and that's certainly an option. For my money though, I mean, look at the size of this function. If anyone's going to make a change to this function, I really want them to actually write the tests themselves and prove that they really understand it before they modify it. So for a function of this size, I generally wouldn't include the unit test in my actual commit, but obviously I would write the test and would confirm that it's working. It's just not something that I'd add into the code base, because I'd rather keep the tests where they need to be, testing the things that are actually live. Hey, one last thing that's kind of interesting here. So we're doing a test against the target here with star mid. Now, if you remember the original code had an equality test, and then it had a comparison test. And this code, we're not doing that. We've got one comparison, but there's no test for our equality. In fact, our test for equality is right here at the end. Now, you might say that what we've done is we've made the worst case worse by having more invocations of this function. So I mean, you imagine if n is 1024, so in our worst case, we're going to be calling this function 10 times. Now, the thing, and I think obviously you'd actually have to profile this to be sure, but what's really happening here is if you look at the cache access, right? So we're accessing, in the worst case, we're accessing this variable, the same variable, 10 times. Now the first one is obviously slow because it's cache miss, but then the other 9 are going to go incredibly quickly. In fact, we're going to get great branch prediction through here. There's a good chance this will be the tail caller optimizer is going to kick in, and we're going to get a very slow first case, and then the 9 additional calls are going to go really quickly. Compare that if we did put a test for equality in here. Now, the problem with this is our worst case is now the one where this mid is like striding across the data. And what we've got is 10 cache misses in a row now, and we've actually put an additional comparison in here. So our worst case is actually the 10 cache misses, and we've actually slowed that case down by putting an additional branch prediction in here, which the compiler has to go and deal with. So I actually prefer this the smaller code here. We've just got the 2 paths rather than the 3. I think it runs faster. Obviously it fits in the iCache a bit better, and yeah, it's sometimes counterintuitive when you're optimizing for the worst case. These days, often the worst case is related to memory rather than instruction counts. Just one last thing before I go. Here's the original code. And you can see, I mean, it's pretty much taking, just this function here is pretty much taking up all of my screen here in Chrome. Jump across to my text editor here. You see it's only taking up about half the vertical space, even though I've got a much larger font size. My glyphs, for example, here's my equals operator. Compare that with the the equals that's stuck in here. And even though it's kind of like a similar size on screen, I find it anyway, that it's easier to interpret these with a much tighter packing, but with a much larger font size. Anyway, that's all I got time for today, so I hope you enjoyed this. If you have any comments, I'm sure you've got lots, please leave them down below. Thank you.